October 3rd, 2025. An interstellar visitor named Tri-I/Atlas sped by just zero point 0.2 astronomical units from Mars. Dozens of telescopes were ready for observation, but the only public evidence was a few faint signals extracted from the night images of the Perseverance rover by two independent analysts. The promised data from the orbital stations of Mars, NASA, the European Space Agency, as well as China and the UAE, remained a mystery. And this major space event since the recorded heat was defined by the fact that no one could confirm it. Have we managed to glimpse the truth of the interstellar comet, or has the closest look already slipped away from us forever? The tasks for planetary science and our readiness for what lies ahead have never been higher. On October 3rd, 2025, the spacecraft Atlas flew past Mars at a distance of just under 0.2 astronomical units, about 29 million kilometers. This distance, close by interplanetary standards, provided the comet with a rare position for scientific observations. Never before had an interstellar object approached the planet with such a coordinated group of orbital and rover missions ready to capture it. The Mars Orbiter, Mars Express from the European Space Agency, Hope from the United Arab Emirates, and Tianwen-1 from China received last-minute observation requests. Each mission team adjusted their schedules, recalculated ephemerides, and prepared to capture a visitor from beyond the solar system as it raced past Mars's orbit. The opportunity was fleeting. At its closest distance, the Tri-I/Atlas raced across the Martian sky at a speed unmatched by any ordinary comet. The geometry was ruthless, a narrow window, just a few days, and a goal rapidly slipping into the bright light of the sun. For planetary scientists, the promise was clear. High-resolution images from orbit could reveal the structure of the coma, possibly even separate fragments if the core began to break apart. Spectrometers could capture unique chemical signatures that distinguish interstellar ice from local comets. All available means, from rovers to deep space orbital probes, were engaged at maximum capacity. The calculations were simple. A well-calculated image or spectrum could answer questions about the origin of the comet, its chemistry, and the processes forming bodies from other star systems. The risks lay in the possibility of seeing an untouched sample of galactic material to test theories about planet formation and directly measure the properties of an object that began its journey light years ago. As the flyby approached, expectations reached their peak. The world awaited a stream of data, and perhaps a clear glimpse into the unknown. A faint, scattered signal in the Martian night sky was all that the Perseverance rover's mass observation camera captured during the hours after the closest approach. The first to extract and publicly confirm this discovery was Stephen Burns, a geologist and experienced amateur analyst, along with Simon Stim III, known in planetary visualization circles for his methodical approach. Working independently, they uploaded raw footage from the Navcam Z camera from NASA's public archive just hours after the data was transmitted. The process was simple in concept but required high precision in execution. They combined dozens of long exposures, aligned them against the starry background of Mars, and methodically suppressed noise until a faint point of light appeared at the predicted coordinates. The resulting work is not a dramatic photograph. It is a calibrated collection of images, annotated and placed on the internet, showing a small, slightly blurred spot surrounded by soft light. The coma, blurred and almost lost in the background, corresponds to the expected position of the Object 3 I/Atlas, calculated based on its orbit before the flyby. No flashes, no sudden brightness increase, just a subtle confirmation that the object crossed the field of view of Perseverance exactly at the time and place it was supposed to be. Burns and Stim III released their results cautiously, emphasizing the marginal strength of the signal and the absence of visible structural features. Their annotated images posted on social media contained overlays of predicted comet positions and links to their calibration scripts, inviting a broader community discussion. In planetary science, such a discovery is not just a technical exercise. This is evidence that even under conditions of embargo and official silence, a careful analysis of open data can yield real results. The weak central point in the collection of images of Perseverance remains the only ground confirmation of passing through 3 I/Atlas. It is neither a breakthrough nor a disappointment, but a testament to what is possible when open data meets persistent curiosity. The examined path to weak detection. 3 I/Atlas begins with images from Navcam Z, each of which is a 39-year exposure, made under the Martian night sky. On October 3rd, 36 frames were recorded, and on October 4th, another 40. Analysts extracted raw data from the NASA archive, matching each scientific image with the nearest dark frame to subtract sensor noise pixel by pixel. Next came the corrections of the flat field, using calibration files to account for pixel sensitivity and dust on the optics. The next obstacle was aligning the frames. Each image of the star field was aligned with the projected star catalog oriented towards Mars, correcting the rover's orientation and the slow drift of the Martian sky. Subpixel adjustments ensured the alignment of even the faintest stars in the aggregate. Rejecting emissions, sigma clipping, and median filtering removed cosmic ray impacts and sporadic hot pixels, while masking marked any residual artifacts. With a cleaned and aligned set of images, the analysts combined them using both median and mean approaches to maximize the signal-to-noise ratio. The background sky was modeled and subtracted, revealing sources just above the detection threshold. The resulting set of images revealed a faint, slightly blurred point in the predicted coordinates for the Tri-I/Atlas, corresponding to the orbital calculation considering astrometric error. Photometric analysis confirmed that the signal's brightness significantly exceeded the noise level in the stacked image. The detection passed the standard signal-to-noise ratio check and was independently confirmed using open scripts with all calibration steps and parameter files published for reproducibility. The result became a transparent and reproducible process, capable of withstanding scrutiny and minimizing the risk of noise in the signal. Rumors spread faster than data. As soon as weak signals from the Navcam Z camera of the Perseverance rover began to circulate, claims of brighter and clearer traces in other rover images quickly emerged. The thinnest trace on a frame from the Perseverance navigation camera, taken on October 3rd, became the most viral, declared as evidence of an interstellar visitor visible to the naked eye. For several hours, planetary forums filled with annotated screenshots and speculative topics. However, the data did not match. Emily, a planetary geologist known for her thorough checks, ran the coordinates through the JPL Horizon system. The path and timing of the footprints matched Phobos, Mars's inner moon, with precision to fractions of a degree. Its speed, orientation, and apparent elongation completely aligned with the predicted nocturnal trajectory of Phobos during a long exposure of the navigation camera. The verdict spread quickly. The viral trace turned out not to be an interstellar object 3-1, but a familiar satellite caught on camera. The second round of discussions focused on the frame from Navcam Z from October 2nd, where a bright, rapidly moving trace was seen, which seemed inexplicable. The analytical enthusiast measured its angular velocity and compared it to the predicted motion of 3-1. The result was obvious. The trail crossed the field of vision in less than a second, at least 10 times faster than the expected speed of the comet. The brightness profile in motion indicated a nearby object or sensor artifact, not an interstellar comet 30 million kilometers away. Emily and others published overlays showing discrepancies in both speed and the supposed path across the sky. Most observers from the community accepted this diagnostic data, refocusing on the weak, expected signal in the calibrated stacked images. This episode left a lesson. In planetary science, every trace requires auditing, data verification, speed checks, and artifact filtering before speculations gain traction. Tools are available, the process is transparent, and the community, when mobilized, can debunk myths as quickly as they spread. The Martian orbiters were ready. The Martian Reconnaissance Orbiter with a high-resolution camera could, in principle, provide the clearest images of an interstellar object from another planet. His narrow field of vision and high sensitivity made each exposure a risk, dependent on accuracy and timing. Mars Express, equipped with multispectral cameras and the Amiga spectrometer, offered a different power: extensive scans for volatile gases and compositional signatures in the coma. The orbital spacecraft, equipped with Nomad and CAS's instruments, was ready to capture both images and high-resolution spectra in search of chemical signatures that could distinguish Comet Tri-Ether Atlas from local comets. The United Arab Emirates spacecraft HOPE and China's Tianwen-1 expanded their observation area, each providing a wide monitoring angle and potentially additional spectral data. The technical capabilities were real. The orbital spacecraft had a unique ability to observe the Tri-Ether Atlas at its closest approach, unlike any telescopes on Earth or nearby that were blinded by solar geometry. Theoretically, high resolution could allow one to see the structure of the coma or notice fragments if the comet is breaking apart. The Omega and Nomad tools, designed to detect weak gases, could capture traces of unfamiliar molecules or rare isotopes, providing the best chance for a breakthrough in understanding composition. Each instrument team adjusted their parameters for the best signal-to-noise ratio, balancing exposure time, onboard data compression, and the risk of detector overflow or target loss. As of October 7th, no high-resolution images or spectra from any Martian orbiter have made it into public archives. Ordinary quick reviews, press briefings, and even raw thumbnails remain under restriction or delayed due to processing bottlenecks. Silence is not a result of lack of effort or observation. It is the outcome of an embargo policy, the accumulation of calibrations, and this time, a governmental shutdown. The world waits, knowing that the most important data may already exist, locked behind institutional verification. Directing a spacecraft towards a moving target millions of kilometers away is an exercise in calculated risk. The ephemerides for the Tri-Ether Atlas were updated daily, sometimes even hourly, as new measurements refined the comet's trajectory. Each mission relied on these changing forecasts for planning their shooting sequences, but the process was far from automated. Orbiters like the Mars Reconnaissance Orbiter and Mars Express had to deviate from their routine targets, often by several degrees, without real-time feedback to confirm they were aiming at the right patch of sky. The tool commands programmed exposures in open mode, meaning each image was a leap of faith. Aim, shoot, and hope. An object crossed the field during the scheduled window. The planning of deep space communication added another layer of fragility. Every data transmission from Mars is a negotiation. Scientific data from several missions, routine telemetry, and urgent commands all compete for limited bandwidth. Even when the sequence was performed perfectly, raw images could remain in memory onboard for hours or days, waiting for their turn behind higher priority transmissions or delayed due to the availability of the ground station. A missed window or a few minutes of deviation in ephemeral data could mean the difference between a historic discovery and an empty frame. The reality is this: the absence of real-time tracking, no second chances, and the inability to confirm success until the data returns to Earth. These limitations are not due to poor planning or technology. These are the practical limits of operations in deep space, where each observation is a balance between prediction, measurement, and the expectation of data transmission. The line between successful capture and failure is embedded in the process itself. Comet 3 and Atlas. The world waits not out of secrecy, but because the mechanics of interplanetary observations are as merciless as space itself. Solar geometry draws a harsh line. With the beginning of October, 3 and Atlas approaches the highest conjunction. On October 21st and 22nd, it will be almost directly behind the Sun from Earth's perspective. By the second week of October, the distance between the objects decreases to limits unsuitable for any telescope. A black screen is not politics, but orbital mechanics. From mid-October to early December, all ground and most space observatories are forced to suspend observations. The perihelion, the moment of closest approach to the Sun, occurs on the 29th and 30th of October, right in the midst of this blinding light. The most active phase of the comet, the possibility of outbursts or fragmentation, occurs when Earth is blind to it. Meanwhile, the silence of the Mars orbiters does not indicate secrecy, but rather a process. The visualization and calibration teams in the Jet Propulsion Laboratory face difficulties. Each raw image must be checked for cosmic ray hits, hot pixels, and subtle registration shifts. The risks increase when tracking a faint, rapidly moving target. Standard methods, tuned for slow landscapes, fail when an object crosses the sky at tens of kilometers per second. Even a slight misalignment or missed artifact can create a ghost, a false fragment, or destroy real detection. Counting is simple. Releasing an uncalibrated image means risking the emergence of another viral myth. Waiting for thorough verification means facing accusations of delay. Internal embargoes, accumulated calibration issues, and the coinciding government shutdown only exacerbate the gridlock. While the world waits, not for concealment, but for proof that can withstand scrutiny. Only then will the next image gain real significance. The working hypothesis remains unchanged. 3 and Atlas is a natural interstellar comet rich in carbon dioxide with only minor or no traces of dimer. the classic green coma marker observed in most comets in the solar system. The temporal reports hint at an unstable mixture, and in some spectra, there may be an excess of metals like nickel. However, no breakthroughs in composition, confirmed by reviews, have appeared yet. The definitive proof will not come from speculation, but from spectra verified by instruments or time series with a high signal-to-noise ratio, data that can confirm or deny the scenario of a natural comet with chemical precision. Since ground-based telescopes will be blind until early December, attention shifts to several available observation tools. The LASCO C3 coronagraph from SOHO will filter solar glare until the end of November. His brightness limit is high, 8th or 9th grade, so only a sudden flash or unexpected increase in brightness can bring 3 Atlas into view. The JUICE spacecraft, launched by the European Space Agency and on its way to Jupiter, may have a brief opportunity in early November for deep space imaging. The success of this operation will depend on the geometry, timing, and whether the fading glow of the comet remains within reach of its instruments. No official statements have been made regarding confirmation or the date of results publication. The calendar is free. Monitor any images from SOHO C3 from late October to late November. Keep an eye on news from ESO and JUICE in case results emerge in early November. By the end of November or early December, ground-based telescopes will regain access to observations, and major observatories along with experienced amateurs will be ready to resume comet observations if its brightness allows. The threshold for confirmation is set. Only direct evidence, supported by instruments, spectral lines, high signal-to-noise ratio images, or time series, can answer the question. The lesson is learned. Without more telescopes beyond Earth, the next interstellar visitor may pass unnoticed, hidden in a blind spot of geometry. To date, the only public discovery is a faint overlay image obtained from the Perseverance camera, calibrated and released by independent analysts. High-quality images or spectra from Mars orbiters have not yet been published. As the Earth enters a shadow zone due to the solar conjunction, official data from NASA, ESA, and other agencies remains pending, with critically important details about composition and structure still unavailable. Before the appearance of new images or spectra, whether from SOHO or renewed ground observation in December, the most compelling evidence remains a solitary weak signal, and the question of what makes the Tri-Atlas unique remains open.